All right, so thanks everyone for being here today. I'm going to be presenting my dissertation on integrating trait and neurocognitive mechanisms of externalizing psychopathology, a joint modeling framework for measuring impulsive behavior. All right, and so to begin, the rough outline for today is I'll talk about what externalizing psychopathology is and how it develops over time. And then I'll talk about the typical ways that we might measure how impulsive or externalizing psychopathology in the lab, and the problems that are associated with those approaches. And then 3, 4, and 5 here are essentially just building off of the traditional approaches and proposing a sort of different way to approach those problems that I think do a better job of answering the questions that we have. So to begin, externalizing psychopathology, when I say that, I'm really talking about psychological disorders that are characterized by high trait impulsivity. So trait impulsivity is an individual difference, so we all have some level of it. And it consists of a preference for immediate over delayed rewards, right? So if you've ever heard of like the marshmallow task, I give you one marshmallow now, and if you don't eat it in the next 15 minutes, I'll give you a second one. So that type of preference for immediate over delayed rewards. Failures to plan ahead or think about the consequences of one's actions. And then generally just having difficulties regulating my emotion and being able to make self-controlled decisions. And many decades of research have come together into what I think is a very nice conceptual diagram here of how externalizing psychopathology develops across the lifespan. And first I'll direct your attention toward the bottom, where we have development from preschool onto adulthood across the bottom here. And then underlying all of what we observe behaviorally, we have some traits, like trait impulsivity is one, and then just ability to regulate emotions is another. But then what we observe, so we don't observe trait impulsivity. Instead, what we observe across the lifespan are behavioral syndromes. And so these are things like ADHD in childhood, specifically the hyperactive impulsive presentation and not the inattentive presentation of ADHD. And so this form of ADHD is more characteristic of like fidgeting a lot, not being able to stay seated, running on a motor, that type of thing. And what can happen over time is that ADHD in childhood can progress onto more severe forms of externalizing disorders, depending on both the underlying vulnerabilities that a person has, so the individual differences in their characteristics, but also the environment that they are in when they're behaving. And so different types of what we could call these mediators, these environmental mediators, can actually push you along this trajectory. But I think what is made clear by all of this is that the mapping between underlying traits or mechanisms or whatever we think underlies observed behavior and behavior itself is actually not one-to-one. It's rather complex, right? So, not only do I have to have high trait impulsivity, I have to not be very good at regulating my emotions. I have to encounter certain environmental contexts in order for me to get pushed along this trajectory. And so figuring out who will and who won't progress through this trajectory is quite challenging. And so that's one of the things that really motivates a lot of my research is this idea of how do we link the underlying mechanisms that we think are responsible for behavior to observed behavior itself. And I first start with what I think we shouldn't do. And so traditionally, what we might do is people will come into the lab and we will collect information on their impulsivity or self-control. And what we want to do is create a quantifiable metric, right? So it's similar to how you take a test or an exam. You get like an 80% on a math test and you sort of get ranked relative to other people. We want to be able to do the same thing with impulsivity or self-control. And typically there are a couple ways we might do this. One is a self-report measure. So if you've ever filled out a questionnaire where they're often Likert scales where you'll say, how often do you do this impulsive behavior? Never, rarely, occasionally, very frequently. And those might be scored 1, 2, 3, and 4. Right. And what we'll do is we'll collect a bunch of those questions and then sum them all up. And that will be your sort of score. And so that's one method. And then another is behavioral measures. And so behavioral measures are a little different. It might be a cognitive task. It might be like a puzzle solving game, some sort of computer game where you're scored based on how you perform. And how you perform can be thought of in very different ways. It might be, how many times you perform the right action in the task. It could be like how long it takes you to respond to a stimulus. And usually what we'll do at the end is we'll extract, the percentage of times that you made the correct action or the average time that it took you to respond in a task. And so at the end, we get some quantifiable, some number that we use to quantify your impulsivity. Now, the problem is if we have the same people do both of these, self-reports and behavioral measures, if one says that you're very impulsive, often that's not the case for the other. And so they don't show high correspondence. And so one of the questions that really drives this first study I'll talk about is why is this the case? And there's been a lot of work on this, but one of the reasons that has been discussed quite a lot recently is that behavioral summary measures, like the average response time or the percent correct in a task, they have a low test retest reliability. And what this means is that if you come in today and you go through the task and I give you a number, and then you come in next week and you do it again, the results are very different. So it would be like if you come into the doctor's office and you're giving a diagnosis, but then you come in next week and you don't get that same diagnosis. That's not good. We want something that's stable, that can tell us something specific about you, and not something that's noisy or uncertain or filled with error, we might say. And so when I say low reliability, that's what that means. And this paper published by Hedge, Powell, and Sumner in 2017, they essentially showed that for a bunch of very popular behavioral tasks used throughout psychology and neuroscience, that the behavioral measures have low test-retest correlations. And so this is a problem when we want to make inference on individuals with these measures. And this has since been replicated and extended. Here's another study where this is all self-control impulsivity measures. And on the left, we have behavioral tasks in these orange. And on average, across all of these different behavioral tasks, the test-retest correlation is about a 0.4 or a 0.5. And this is a number that ranges between 0 and 1 typically. And closer to 1 is usually better. We want these measures to be somewhere around 0.7, 0.8, 0.9. And so 0.4 is not good. Whereas the self-reports in blue over here, they do show pretty good performance, so about 0.7, 0.8. And so this is an issue. And so the question is, well, if summary stats perform poorly, then what do we do instead? And so what I've proposed is that we should use what I call generative models. And I'll describe what that is here. First, let's set the context. So if you come into the lab, you might have, like if you go through a behavioral paradigm, a behavioral task, it might look something like this. So you can imagine you're sitting here in this chair, you have this computer, and what you're seeing here is the word blue, but colored red. And the goal of this task, this is the Stroop task, is to tell me the color of the word, right? So here you're supposed to say red. And what you'll notice is that the color of the word and the word itself are incongruent. They don't match. Whereas you can imagine this could be the color blue. And what happens is that on average, it takes longer for people to make a response to the incongruent pairs than to congruent pairs of the stimulus features. And the difference between the average response time in seconds that it takes for you to respond to the incongruent versus congruent trials, if we collect a bunch, is what we call the Stroop effect. And so this was one of the things that was published in that study that I was talking about earlier, that Hedge paper. Basically what you do is you take the mean of the response times in each of those conditions, take the difference, you have people come in at time 1 and come in again a few weeks later. The test-retest correlation is about 0.5, so it's pretty bad. But one of the problems with this approach is that when we take the mean like this, we're actually ignoring sources of uncertainty at the individual level that actually very much can bias our inferences. And so what I have proposed instead is that we use generative models of the decision process so that we can actually not only account for that uncertainty, but also we get more theoretically useful information out of our measures. And so here what I'm showing you is before, we just took the mean of the response times. And here, if you can imagine the gray are the observed response time distributions, if you just plot them all out. Now we have this red curve is sort of our model of how we think the response times arise. And here I'm using this log normal model. And it looks sort of like this, where you have these two parameters, mu and sigma, and they control just the shape of this model. And if we fit the model to the data in each of these conditions, and then we take the difference in the parameters, now we have a difference in these mu and sigma parameters between conditions, and those are now what characterize the Stroop effect. So your behavior is determined by these parameters, and we can think of these in terms of like cognitive mechanisms or psychological meanings. So mu is often interpreted as a sort of difficulty, and sigma as a sort of noise in the decision process. Okay, so for a generative model, we'll do this, and then what we can also do is we can estimate the correlation in those Stroop effects simultaneously while we're estimating the person level effects. And so what this actually allows us to do is it allows us to account for measurement error that the two-stage approach over here ignores. So if you see, we have these two contiguous steps, whereas in this approach, it's all sort of one model. And by doing this, we actually get a better estimate of how stable these behavioral performance metrics are over time compared to these alternative approaches. And this is all based on the joint modeling framework developed by my co-advisor, Brandon Turner. So I thought I would mention that here. All right, and so that's all theoretical. It should work, right? But what we did was we reanalyzed data, kind of comparing the two-stage approach that I showed you there on the left to the generative approach for a variety of different tasks. So I'm not going to go through all of these here, but I just wanted to give you sort of a brief overview of all of the different tasks that we analyzed. And here we fit 3 different generative models. And one was the log normal model that I showed you there on the previous slide. But I won't get into detail on those models. I think the most important comparison will be to show you how the two-stage approach compares to the generative models. And that's what I'm showing here. So here on the x-axis, we have the test-retest correlation, which should be somewhere between 0 and 1. And then here we have the mu parameter at the top for each of the studies, and then the different colors are the different models. And so what I want to bring attention to first is if we focus on this top panel, the two-stage approach represented by the correlations here and the dots and then the uncertainty intervals in the bars. On average, you get about 0.3, 0.4 test-retest correlation across all of these different tasks that we reanalyzed, whereas the generative models are performing much better, like around 0.7, 0.8. And you see sometimes you see this for the sigma parameter, not as much, but mu, this parameter again reflects how difficult that the stimulus is. And so this is usually what we're making inference on. And so basically what we showed with this work is that generative models can indeed be used to improve the reliability of behavioral measures, or at least they can give us estimates that that better reflect what we're actually interested in these tasks. Okay, and so that's great, but what I was talking about before, I showed you this really complicated diagram at the very beginning where a person becomes more impulsive over the course of the lifespan. They have some underlying vulnerable traits like trait impulsivity or emotion dysregulation, but then they also encounter different things in their environment, like the parenting environment or who they hang out with, the availability of substances of abuse in their environment. And so that's rather complex. And what I just talked about was this simple task where you like press a button on a screen, right? And so then how can we actually use some of these models to capture more complex person by environment interactions, which are really important for understanding externalizing psychopathology? And what I suggest is that we should use theory to guide model development. And to show this, I'll walk through an example of a study that we conducted where we took insights from this dynamic developmental theory by Sajvolda in 2005. And in this theory sort of proposes that in children who develop ADHD, one of the key factors is a hypo-functioning dopamine system. And dopamine is a neuromodulator in the brain that's responsible for quite a lot. It modulates the activity of other neurotransmitters, as well as having large effects itself on learning. And the basic idea here was that if a person has a hypo-functioning dopamine system, then this can lead to a preference for immediate over delayed rewards. And the argument is here. I'll walk through some of the pieces here because I think they're important. So there was some foundational work that was done back in 1997. This paper by Wolfram Schultz was published. And basically what they showed was that dopamine neurons in the brain respond to unpredicted rewards. And so here at the very top panel, we have all these rows are different dopamine neurons. And when you see a dot, that's when the dopamine neuron is spiking. And at the top, this is just aggregates of them. And then here, this bar is when this monkey was given like a sip of juice, an unexpected reward. And what you see is that these dopamine neurons, they all spontaneously or simultaneously fire in response to that unexpected reward. And then compared, and then so what happens though is if something predicts that reward, so say I shine a light in your eye before I give you the reward, or I make a tone sound, or show you a certain picture before I give you the reward, and I do that repeatedly, what ends up happening is dopamine sort of goes back and begins to respond not to the reward itself, like the juice, but to that predictor of the reward. So after I see the stimulus unexpectedly or the light unexpectedly, then my dopamine neurons spike. And that's what's shown here in this middle panel. And then if you don't show the reward after you show the stimulus and you expect to see it, you get a dip in dopamine. And so this is really important because it shows that dopamine actually functions as a learning signal in the brain. And we can actually, with some simplifications, we can develop computational models of how this works that give us some insight into how dopamine activity can relate to a preference for immediate over delayed rewards. And so for example, so here, if we pay attention to this panel over here, I'm basically making a simplified version of the figure I just showed you, where we have this bar here is supposed to be a stimulus. This dot at the end is like when you receive a reward. And with repeated pairings, what ends up happening is the expectation in black here propagates back towards the stimulus that predicts the reward. And in theory, I learned to predict the reward given the presentation of the stimulus. But I have this control panel, and then I'm showing this ADHD model of a panel where the only difference between these two is that I generated the ADHD data here with a lower learning rate. And so it's just taking longer for, so what that's supposed to represent is this hypodopamine activity. So the dopamine isn't responding as much. This leads to this lower learning rate. And in effect, this means that the expectation propagates back more slowly. And what you can actually do is if you can actually derive from this, like how much do people discount people learn to expect later rewards, but if it takes longer, if you have a lower learning rate, you can actually derive a discounting curve, which says, after learning so much, or after sort of observing many pairings of a stimulus with a reward at different time intervals, on average, how much do I discount to rewards at specific delays? And you can actually derive a curve from this, with this discounting factor when it's at 1. So with increasing delays on the x-axis, y here, when it's 1, I'm not discounting at all. And so for the control model, you can see like across all these delays up to 25, I'm not discounting a reward. But then once the delays get up to about 50, here, like maybe 50 minutes, 50 hours, the time interval is kind of irrelevant here for now. I'm discounting the reward by 50. So this is like, if you, if I were to give you $800 now versus $800 in 20 years, you'd probably prefer it now. And this is because as time increases, the length between now and the reward increases, the value of the reward sort of diminishes. And what we're seeing is that from this, you can see that the control model actually is sort of assigning more value to rewards occurring later in time than the ADHD model. And this will be important when we come back. But basically what we're showing here is that learning through this dopamine, this neurocognitive mechanism with dopamine activity can actually explain preference for immediate over delayed rewards and how that arises. And so what we wanted to do was look at this in the context of externalizing psychopathology. So if learning is this important process, people learn to prefer like good versus bad actions in their environment. How can we actually measure this in a laboratory environment? And so we used the Iowa gambling task, which looks kind of like this on the screen. So you'll have these 4 different decks, A, B, C, and D, and you're just told at the beginning you have 100 selections that you can make. So you can pick A, B, C, D, however many, you just get 100 total selections that you can make, and you just want to earn as much points as possible. And what happens is, I'm showing you here the first 10 selections from each of the decks. What happens is A and B look pretty good at first. You make lots of money, but then you encounter enough loss that in the end, if you were to keep picking them, you actually lose money. Whereas C and D, they look okay at first, but over long term, you actually gain money by picking them. And so the person is actually tasked with learning learning that C and D are optimal decks. And so you should develop a preference for those decks over the course of the task. And what we often find is that in groups with externalizing psychopathology, they tend not to perform as well as controls or people without externalizing disorders. And so we were interested in looking at this, and specifically we looked at it in the context of substance use disorders. So we had 48 control participants, these are all adults, 38 with a history of chronic amphetamine use, and 43 with a history of chronic heroin use. And we developed a learning model that could actually perform the task similar to how people do. But the model has many different parameters. So, I was talking about like mu and sigma in our models earlier before. Now we have 5 different parameters for the model for each person. And but for our purposes, we're really most interested in the positive learning rate here, the reward learning rate, and the punishment learning rate, which control how much you learn from the gains versus the losses. And so what's really interesting here, so this is an example of like what a healthy participant's sort of simulated behavior might look like. So I'm generating model behavior from the model with this. So I've set these parameters to certain values and just had the model play through the task itself. And what happens typically, what we observe in healthy participants, is that you develop a preference for deck B because it looks really good at first, but then you encounter this really big loss that makes it not worth it. And what typically happens then is I start to not like deck B, and instead I begin to prefer deck D, right? And so we have these pretty complicated dynamics that occur. But what happens sometimes is if I, for example, if I lower the punishment learning rate, so if I'm not sensitive to this large loss, then what ends up happening is I never unlearn my preference. So I continue to make bad decisions, even though the environment is responding in a way where I should change my behavior, but I'm not, because I'm not sensitive to punishments. And so, thinking back, we talked about how lower learning rates could lead to kind of a preference for immediate over delayed rewards. And specifically, a lower punishment learning rate can actually then even bias things even further to make me prefer not only immediate over delayed rewards, but also immediate rewards that potentially have long-term consequences. So you can see that we're beginning to capture more of the impulsivity as we refine this model further. And so what we did with this is we took the data, and just as I won't have time to get into this in detail, but here's the actual empirical data across the group for the control group. And what you can see is that on average, they begin to prefer deck D. And this is the simulations from the model showing that it captures those trends quite well. And then also for the amphetamine group, they tend to prefer deck B, and then they sort of don't differentiate B and D very well towards the end. And the model is also capturing this behavior. And then with the heroin use group, kind of similarly, but there's more differentiation between D and B, and the model captures that. And so what we can actually do then is we can compare the parameters of the groups and see, what might be different across the groups that's leading to these differences in behavior. And what we actually found was that this negative learning rate, as I was showing up here, was lower in the substance use groups compared to the control group here in pink. And so what this means is that the substance use groups simply have this lower punishment learning rate. So they're learning less from punishments in their environment relative to controls. And that is, or the inference here is that is what's responsible for the bad decision making in the context of this task. So in general, the conclusion here is that these generative models, we can use them to capture these theoretically relevant mechanisms that are in principle not possible to detect if we were only to look at how many good versus how many bad deck selections did they make. And so this is why I think these models can be very useful. And that's very, very interesting. And I think, then we wanted to look at, how can we then use some of these models, that what I just showed you was a group comparison. So we compared the groups, but we didn't actually look at, does one person's, as their negative learning rate increases, does their trait impulsivity also increase or something like that? And those types of questions are individual difference questions, which are related to the first study that I talked about, and also are very important if we want to understand who and why a person might develop further externalizing disorders. And so one of the ways that I think we can approach this question, and I'll demonstrate this in the next study, is that we can include all of this information into a single model so that we can estimate relationships between traits and behavioral mechanisms simultaneously in a way that sort of respects our theories. And so the sort of theory, the question that motivated this last study that I'll talk about is called reinforcement sensitivity theory. And it sounds, the description here sounds kind of complicated, but it's actually quite simple. And I'm sure you've all experienced something like this where, I might have this urge to do something impulsive, but then I get maybe a rush of anxiety that sort of inhibits me from doing that. Or, you can think of various different things. So we could imagine that, maybe I would go talk to this person at a social gathering, but I get this urge of anxiety, and that sort of stops me from engaging in any behavior. I'm thinking of all these risks that might occur if that happens. And so that's basically what reinforcement sensitivity theory predicts. And so we were interested in looking at this in the context of the lab, which is is that, if I take people and I look at how impulsive they are, and then I look at how anxious they are, does that anxiety actually inhibit impulsive behavior? And there's actually lots of reasons this is important for understanding the progression of externalizing psychopathology. So, for example, if adolescents actually have externalizing disorders, so they're diagnosed with ADHD or oppositional defiance, conduct disorder, though if they also have high trait anxiety, they tend to have less police contacts, they get along better with their peers, there's less neural differences in the gray matter structure of the brain between them and control groups. They also respond better to treatment, as some studies have shown. So if we go back to that diagram that I showed at the very beginning, we could add this isn't technically correct, but we could add the anxiety to this as well. And then kind of thinking again, when I was talking about, this dopamine theory and how that relates to discounting of like preference for immediate over delayed rewards, we showed how that could arise. And a lot of times though, when we're thinking about measuring immediate over delayed reward preferences, we actually can measure that directly with these, what we call delayed discounting tasks. And so this is a task wherein I'll show you, I'll give you $10 now or $15 in a week, which would you prefer? And so if you ask people a series of questions like this, you can actually estimate a parameter called K that tells us how much, as we increase the delay here, do you discount this reward, right? So $10 now is just worth $10, but then if I were to say $10 in 100 days, it loses value slowly. And if you have a low value of K, that decay is a little slower, so that's less impulsive. But if you have a high value of K, then it happens very rapidly, such that even a small increase in the delay can lead to a large change in preference. And so this is the framework that we used. And to look at this question, we had 3 different groups of participants with various levels of impulsivity. So our first group was just undergrads that were unselected. We didn't, say they had to have anything specific to come in. And then we had 800 Amazon EMS workers who were screened in for problematic substance use, and then 35 people who were diagnosed with substance use disorders by trained clinicians. And the measures that we use, so we looked at trait impulsivity with this non-planning scale of the Barrett impulsiveness scale, and then we used the state trait anxiety inventory to measure state anxiety, so how anxious people were when they were performing the task, and then delay discounting, which was the task that I just showed you. It's a series of choices between immediate and delayed rewards. And to analyze this data, we thought about the various different dimensions of this task. And so there is a reward dimension and a delay dimension, right? And so the reward here, so we can imagine that there's like $100. So A is 100 in this case. And one of the things that's really interesting about a lot of previous research is that we know that as the monetary value increases, there's sort of diminishing subjective utility. And so, for example, what can happen is the difference between $1 and $2 is psychologically much larger than the difference between $800 and $801. And so we can actually capture this with this subjective utility curve, which basically says that as the true amount increases, that subjectively the amount starts to diminish. And alpha is a parameter that controls this. So if everyone has their individual alpha, if I have a really low alpha, it means that so this gray bar down here, even differences, like true differences in $600 and $800 subjectively don't actually change a whole lot. Whereas if I have a very high alpha, the difference between 600 and 800 is still quite large. And so basically when the alpha gets lower, people start to, not really consider, or people are not able to really assign value to different rewards in their environment. And instead, any good thing is a good thing, then all good things are equal. And that's kind of how you can think about this as this gets lower. So that's the reward dimension, but then there's also the time dimension, or the delay. And again, like we talked about, so the delay here and how much the delay reward is discounted. So if it's 0, then it's worth nothing to me with the delay. But if it's 1, then, that's what happens at so if I would give you $10 now, it's just worth $10. But if I give it to you in 100 days, depending on what K is, I might discount that reward by some amount. And so what we can do is we can take these 2 different dimensions and we can combine them. And so, we assume that you assign some subjective value to the monetary amount, and then you discount it by how far away it is in the future. And then if you put these together, what you can see here, so this is an example choice, and dark blue here is And so these are different combinations of the K, the discounting factor here, and alpha, the subjective utility curve. And when you put these together, what you can see is that different combinations lead to different probabilities of choosing the delayed versus the immediate in dark red reward. And what's important to note here is that as K increases, no matter what alpha is, a person is always expected to become more impulsive, right? They're more likely to choose the red here, which is the immediate reward, right? And so this is K is what we think should be related to impulsivity or trait impulsivity. Whereas with alpha, the effect of alpha actually depends on the person's level of impulsivity or their K. If a person is already very impulsive with a high K, right, so they're discounting delayed rewards a lot, if alpha gets smaller, they actually become less impulsive. Whereas if alpha is, if K is lower, they're not very impulsive, and alpha gets lower, then they get more impulsive. And so this is a mechanism through which if alpha is negatively related, so if state anxiety actually decreases alpha, this could actually give an explanation for how, if anxiety, if what it does is attenuate the value of reward. So when I get anxious, it gets hard for me to think of, the potential rewards of doing various things in my environment. So when I'm anxious, I'm not necessarily thinking about how valuable it would be to go talk to the person at a party, or how good it's going to feel to be done with my exam. I'm not really thinking about those rewards. If that's what's going on, so there's a negative relationship between alpha and anxiety, then that could kind of give rise to these predictions that fall out of reinforcement sensitivity theory. And so we fit the models to all of our groups of subjects, and that's actually what we found, was that trait impulsivity was positively related to delay discounting, the discounting rate, and that state anxiety, so the anxiety that people endorse coming into the session, was negatively related to reward valuation, and reward valuation being that alpha parameter. And so what this suggests is that and this is actually consistent with empirical evidence showing that in studies measuring people's neural activity, if you induce anxiety while you're scanning people's brains, you see sort of an attenuation of the reward signal in the brain. And this model can kind of capture that with these parameters. And so basically what this suggests is that for very impulsive people, state anxiety can actually help inhibit certain impulsive behaviors. But if you're not very impulsive, it can actually promote them. And so this is something interesting that I'd like to follow up on in future research. But more generally, what this shows is that generative models can help us jointly model impulsivity and other phenomenon across levels of analysis, so that I can actually make these interesting inferences on, on how impulsive behavior actually relates to these traits or these mechanisms like anxiety that our theories have make specific predictions about. Okay, so those are the studies that I wanted to talk about. Now I just have kind of these two different categories of conclusions that I wanted to quickly go over. And the first is methodological, and the big picture idea here is that I think generative models, they can allow us to test our theories with more fidelity, and that's because they allow us to take our conceptual complicated theories and make them into models that we can then use to actually measure behavior or things in the lab that we can't do that when we only use simple summary statistics like means or percentage correct in a task or something like that. And then there are more important, I think, theoretical points that I've kind of covered here, which are that externalizing psychopathology and that its development is linked to diminished learning from punishments relative to rewards. And so this is actually consistent with a bunch of research showing that, a lot of parents who come in with a child with hyperactive impulsive ADHD, they'll try to punish their child in all of these different ways to control their behavior, and it doesn't seem to work very well. Instead, a lot of the treatments that do work, that are evidence-based, rely on kind of changing reward structure in the child's environment and getting rid of these ineffective punishments. And one of the reasons that that might be the case is because people simply are not as sensitive to learning from punishments relative to rewards. And that's something that we found even in this simple behavioral task. And also we find that people with externalizing disorders have steeper discounting of delayed rewards. And a lot of what I've showed you is specific to substance use, but I'm currently working on some studies that extends a lot of these ideas to adolescents with externalizing psychopathology. And then finally, that last study I showed that anxiety can compete with impulsive valuation by diminishing the value of rewards. And then this can lead to these interactions between impulsivity and anxiety that are predicted by theories. All right, so that is the talk. Thanks everyone for coming, and I just wanted to give a huge shout out to the Beauchesne and my the Beauchesne labs, Hunter, Shadi, Lana, Juliana, Kristen, all of you. You guys are all awesome. Thanks a lot for all your support. And then Brandon Turner's lab as well. I don't have time, I guess, to list everyone's name here, but like all of my collaborators, my mentors, and then of course the Haines family. Thanks a lot for supporting me throughout all of this. But that's all I have. So ready for questions.